Alright, in this lesson we're going to be doing some examples of converting polar form complex numbers back into standard form. So here I've got it as an r-cis theta, and I'm actually wanting it as z equals a plus bi. That's what I want to get to in these cases. So these are the opposite of what we were doing previously. Alright, these are probably a little bit easier because if we remember that cis means cos plus I sine. So here I convert the cos to the cis, to cos pi on 6 plus I sine pi on 6 equals 2, and then I just get my calculator and I work out the cos of pi divided by 6, and I get 0.866 plus I times the sine of pi on 6, and these ones you should know. Sine of pi divided by 6, close brackets, equals a half. So that's all I did. I worked out the cos of pi on 6, the sine of pi on 6, I got them. So 2 times 0.866, 2 times 0.866, 1.73, plus 2 times a half will be 1, so plus I. So there I've got it as a plus b, which is a 1 in this case, 1i. Just to double check, if you actually drew a diagram of this, 2 cis pi on 6 as an argument is up in this quadrant here, and that distance out is 2. So it makes sense that this is our standard form, 1.7. Yeah, that probably fits geometrically, and going up 1, it kind of makes sense. So you can have a double check, a quick check in your mind as to whether your standard form matches your polar form. When I said here that you should know these some of these basic trig ratios, let me just do a little bit of quick revision on that. You may remember that you've got a couple of triangles that you would have seen, I would imagine, in another maths class. 60 degrees, 30 degrees. Remember, 60 is pi on 3, 30 is pi on 6. This is 1, this is 2, this is root 3. This is a standard triangle that you should know. You could work out Pythagoras rule and just see that this actually works. This squared plus this squared does in fact equal that squared. It actually comes from an equilateral triangle, all sides being 2. So 1 plus 1 here makes 2. 2, 2. An equilateral triangle has all angles of 60. So if you've got 30 there, 30 there, cut it in half, and you've only got 30 as part of that triangle. So that's a good way of remembering where this particular triangle comes from. So when you come here and you work out the cos of pi on 6, you can say here, well, here's pi on 6. The cos of pi on 6 is the adjacent over the hypotenuse. So the cos of pi on 6 is actually adjacent, which is root 3, over hypotenuse, which is 2. And if you work out root 3 divided by 2 in your calculator, you'll actually get 0.866, which is what we got in our problem. And then here, the sine of pi on 6, you come to your angle pi on 6, here it is, and you know that sine is opposite over hypotenuse, so you go opposite over hypotenuse. So the sine of pi on 6 is opposite 1 over hypotenuse 2. In other words, 0.5, what we got there. So you should know this particular triangle. It's handy, it makes it quick sometimes. And the other triangle that is useful to know is the one with 45 degrees, or pi on 4. Okay, pi on 4 there as well. So it's a 45-45 triangle. These are 1 and 1. use Pythagoras rule, that means your hypotenuse must be root 2. And so if you had to work out the sine of 45, for example, in a different question, the sine of 45 would be opposite over hypotenuse, 1 over root 2. Same with the cos of pi on 4, sorry. The cos of pi on 4 is adjacent over hypotenuse, 1 on root 2 as well. So these two triangles are very useful when it comes to working geometrically with complex numbers, and in fact when we do vectors. Okay, we'll do one more example of these. These are a bit simpler. Let's have a look at this example here. Let's convert this to standard form. 20, oh no, we'll just go 2 cis 2 pi on 3. Now, I suggest you draw a quick diagram. So this complex number has an argument of 2 pi on 3. Remember, this is 3 pi on 3. This is 0, so 2 pi on 3 is like 2/3 of pi, so it's going to be somewhere out here. This angle here is 2 pi on 3. There's another pi on 3, which would take you around to 3 pi on 3. So I always find it useful to kind of predict what answer you should get. We're wanting z equals a plus bi. If our complex number is out here somewhere, I know that its real component should be a negative. I know that should be a negative, and I know its imaginary component should be a positive. So really I should be getting a negative a plus a bi. So, but anyway, let's keep working this out and see what we get. So we know that cis means cos plus I sine equals, and you can use those triangles that we did previously, but without going into a whole lot of explanation with those. In these quadrants you can work out the cos of 2 pi divided by 3, and you get negative 0.5, so 2 times negative 0.5 plus I, and you can work out the sine of 2 pi on 3, but I can tell you you'll get 0.866 equals, multiplied out, you'll get negative 1 plus 1.732 I. 2 times 0.866 will give you that one. Now let's just double check. Is that what we expected? The real part was negative, the imaginary part was positive. So negative 1 plus 1.732 would make sense that it would take us to that point there. So I'm pretty confident that this would be feasibly a correct answer for that as the problem. It's always good to double check those sorts of things in your mind.